Welcome to my classroom. In this chemical process calculation course, we are almost coming to the fag end of this course. So in this lecture, we are going to discuss about how to make use of psychometric charts for solving numericals. Okay, so we are going to solve some numericals. In the previous two lectures, we have defined what are the terminology associated with humidification, dehumidification, what is adiabatic saturation. So all that we have seen. And in the previous lecture, I have told you how to construct the psychometric chart. What is each line, what it does it represent. I have been discussing the previous lecture. So I hope you have completed those two lectures. Now, once you have gone through that, I hope there is no doubt about what is the to each term, what does it represent in how to make use of psychometric chart. And I have given you all the formulas which are associated with it also, right? So now we are going to solve the numericals. Okay. So in this psychometric chart, in the previous lecture, we have defined what are the each terms associated with it, and we have seen what are the what does each axis represent in psychometric chart, and we have seen how to get data. Like for example, x-axis is dry bulb temperature, y-axis is humidity, and what to do: heating, cooling, humidification, dehumidification, evaporative cooling, sensible cooling, heating and humidifying, cooling and dehumidifying, all that have been explained. And these are the some of the formulas which we should know how to determine the parameters. If partial pressure is known, how to determine molar humidity? It is number of moles of water by number of moles of dry air, which can be written as partial pressure by partial pressure of A by partial pressure of B, where A is water vapor and B is dry air. And if molar saturation humidity, how to define, how to calculate it. We have seen how to determine the relative humidity or relative saturation. It is the ratio of partial pressure by vapor pressure into 100. Okay, and we have seen what is percentage humidity. It's N by Na by Nb ratio at the given condition to that of same ratio at saturation. We have seen how to make use of steam table to if relative humidity is known, what is the corresponding saturation pressure at the given temperature can be taken from the steam table. So steam table where temperature versus saturation pressure is there, we can take the data, which that data can be made use to determine the vapor pressure. For example, relative humidity is known. Relative humidity is equal to vapor pressure by saturation pressure. So we have RH is given, and saturation pressure. If you know the temperature, we will have get from steam table. We will get the saturation pressure. We can determine the vapor pressure. Okay. So and to determine the mass density, if you know absolute humidity, can be taken from the chart, and we can get the specific value also from the chart, and we can determine the vapor density. And similarly, how to get the heat added, we need the mass flow rate, which can be obtained by, if you know the initial volume is given in meter cube, if we get specific volume in meter cube per kg from the chart, we can able to get the mass flow rate. So and H1 H2 are enthalpy value, which can be taken from the psychometric chart, and we can determine the factor. Another factor is bypass factor, which is defined as the dry bulb temperature minus adiabatic dew point divided by dry bulb temperature minus adiabatic dew point. So these are 2 points, 1 and 2. So we can find out the bypass factor. This formula is used. Okay. Similarly, if to determine the sensible heat factor, if this kind of process is involved, so we can know the H1, H2, and H3 can be obtained by drawing a triangle. Where we can get H3 value. Substituting, we will get the sensible heat factor. Similarly, what is the heat extraction or addition capacity is your m dot into H1 minus H2, where m dot is volume by specific volume, which I explained some time back. Okay, that is the capacity of a cooling coil also can be calculated in the same way. Okay, and the amount of water vapor added or removed can be calculated by the mass flow rate into absolute humidity at condition 1 and condition 2, that is initial and final, can be used to determine the amount of water added or removed. Okay, and we have I told how to convert the heat added or removed. Heat capacity can be converted to tons of registration using the conversion factor 1 tons of refrigeration is equal to 211 kilojoules per minute. Okay, so there is another factor called contact factor, is mainly for heating or cooling coil. So this equation can be used to determine the contact factor. Okay, so now we will start solving numericals using psychrometric chart. Okay, okay, now we are going to solve numericals using psychrometric chart. Okay, how to solve numericals? Say for example, take down this problem. So if you look at, assume that the outside air temperature is 32 degrees Celsius with a relative humidity of 60%. So these two parameters, dry bulb temperature and RH, relative humidity, is known. Use the psychrometric chart to determine the specific humidity omega, that is absolute humidity. Okay, so we have to find absolute humidity, we have to find the enthalpy H, we have to find the wet bulb temperature, we have to use the wet bulb temperature TWB and the dew point temperature TDP and the specific volume of the dry air V. Indicate all the values determined on the chart. We have to show the values on the chart. Okay, so that's important. So I have given the answers. Let us see how to get these answers. Okay, so this is the psychrometric chart which we are going to use in our course. So we have dry bulb temperature. I am using this colored chart. Even in black and white, we should able to see the definitions, means the terms, and you have to get the data. Okay, so we have dry bulb temperature in degree Celsius. This chart is only applicable for 0 to 50. Extension is not given. So if you have a numerical involving 75 degrees Celsius, we have to make use of another chart. So remember, we have to use a psychrometric chart at atmospheric conditions. Okay, so we have clearly mentioned it is a simplified psychrometric chart at 1 atmospheric total pressure. So on atmospheric condition operations, we can make use of this chart. So we have specific humidity. Okay, so what to do? First, we have conditions are given, right? What are the two conditions given? So in this problem, 32 degrees Celsius is the dry bulb temperature and 60% is the relative humidity. So 32 degrees Celsius, here dry bulb temperature 32 degree, humidity is 60 percentage given, 60%. So in this 60% line and 32 degrees Celsius, here we have to mark our point. Okay, so let us say this is 35. So middle will be between 30 and 35, 32 will be 32.5 is the middle line. So we have point around here. Okay, so this is a 32 degrees Celsius line, and 60 we have 60% our relative humidity line is here. So there we have a point. So that point we have to mark all the points. Okay, so if you draw a line horizontal to this x-axis, what we get is specific or absolute enthalpy. This point we are getting, this is 15, this is 20, so half of it, it is going to be 17.5. So we are going to have a value more than 17.5. Let me say 18 or 18.5. Okay, so that is the unit is given, grams of moisture per kilograms of dry air. So accordingly we have to write. So if I write in kilogram, it is 0.015, 0.02. Okay, so accordingly we are going to get the value here. So what we have to do, using the scale, you have to draw a line parallel to x-axis, and in between 15 and 20 we have to get the value for absolute enthalpy. Okay, sorry, it's not absolute enthalpy, it is absolute humidity. So what we get here is absolute humidity. Okay, so this is the enthalpy line. So we have to get enthalpy line parallel to this one. Okay, so that will give us the enthalpy. Okay, then how to get a dew point temperature? If you draw a line parallel to x-axis and where it gets saturated, that is like you draw a line up to here in the 100% saturation line. So you get the corresponding x-axis value, we will get dew point temperature. Okay, and if you draw a line, this is your specific volume line in meter cube per kg. It is 0.9, it is 0.87. So if you draw a line parallel to these green lines, we will get specific volume. So what is the value? We have to choose. It is 0.87, it is 0.9. Half of it is going to be 0.87. 885. So it is, you have to take a value accordingly. Okay, you can, what you can do is you can use the scale, make equal 5 divisions, you can take the value accordingly. This is how we regularly we will do with graph sheets. Okay, similarly, next point what we can get is, so if you draw a line parallel to this, we are going to get wet bulb temperature as 25, above 25 degrees Celsius, right? So we can get the wet bulb temperature. And if we have seen that the lines parallel, enthalpy line and wet bulb temperature are the lines parallel to each other. So here it is given enthalpy lines 30, 40, 50, 60, 70, 80. So if you draw a line parallel and extend up to here, we will get wet bulb temperature. That red line, it gives us wet bulb temperature. And if you are extending it up to this enthalpy line, we will be getting it is more than 70 and less than 80. Half of it is going to be 75. It is something more than 75. So accordingly, you can get the enthalpy value using this scale. Okay. So we have a point 32, that's what we're drawing here. So we have a line 32 and we have 60% humidity line. Though when you go towards x-axis, you are going to get the value for this one. And if you are going to what's parallel to this wet bulb temperature, you will get a wet bulb temperature. And if you are drawing a line horizontally here, you are going to get dew point temperature, and here we will get the dew point temperature. So if you go further here, extend it, we will get H line, where we are going to get the value for H. Okay. So in this way, you can check values. So you can get plus or minus values, but what I have observed is the specific humidity is the enthalpy H is 78, wet bulb temperature is just above 25, so it is 25.5, and dew point temperature is around 23 degrees Celsius, and specific volume of the dry air is 0.89 meter cube per kg. Okay, so how I have done, I just explain again. So this is the chart I have taken. So I have drawn a 32-degree dbt line, and it is 60% it is given, so 60% RH line. So there I mark a point and draw a line parallel to x-axis to get specific absolute humidity. It is specific absolute humidity. Okay, and if I draw a line to horizontal and towards left at the 100% saturation line, at the 100% saturation line, corresponding x-axis value gives me the dew point. Okay, so if I draw a line parallel this black line, if I draw a line parallel to these black lines, I will get enthalpy. If I draw a line parallel to specific volume, I will get the specific volume data in the x-axis. And if I draw a line parallel to black lines, I will get enthalpy H value, small h value. What we get here is capital H value. Okay, so we'll get enthalpy data. So those are the data asked, and we are getting the answer in this one. Okay, second problem, assume that the outside air temperature is 8 degrees Celsius. If the air in your room is 25 degrees Celsius with a relative humidity of 40%, use the psychrometric chart to determine if the window of that room which are in contact with the outside will become foggy or not. When it will get foggy, if dew come on the window, we are going to have window. So that is the hint here. The air is in contact with the windows will become colder until the dew point is reached. So if dew point is reached, so we are going to have foggy. So we have to see what is the dew point temperature. That is the question here. Okay. So if you see the what is the dew point temperature, and outside it is 8 degrees Celsius, whether fog will be formed or not. That is the question. Okay. So two data is required to use the psychrometric chart. We have 25 degrees Celsius and relative humidity is 40%. So go for this chart. In this, whatever data is given, that is 25 degrees Celsius and 40% relative humidity is there. So mark those points. So if I mark it, and if I draw a line, so this is the point we have to mark, right, for the given temperature and pressure. So if you draw a line parallel to 100% saturation line and get the line at the x-axis, we are going to get dew point temperature. We can see that it is just about 10 degrees Celsius. We are going to get dew point temperature, which is, so even when the temperature is about 10, we are going to have dew point. So if temperature is further reduced, obviously condensation, that is dew will be there. So we can say that it is the value what we get is slightly higher than 10 degrees Celsius. So it is given that outside temperature is 8 degrees Celsius. So what will happen? There be dew. So at that point, the water vapor condenses as the temperature approaches 8 degrees Celsius along the saturation line, and the windows will become foggy. So that is the answer. So this is a simple question. Okay, what first if you know the dew point temperature, outside temperature, so it is less than the dew point temperature, obviously there will be fog. That is the answer for this question. Okay, and look at this another question. So this major application is about comfort zone. I in the theory lecture I have explained you about comfort zone. So I might have told each person may have feel comfortable at certain degree, but for this particularly mechanical engineering, where air conditioning system, they define this comfort zone as temperature between 22 to 27 degrees Celsius and relative humidity between 40 to 60% is comfort zone. So we try to have such temperature range and humidity range in the air conditioning system. Okay, so this is the definition of comfort zone, which is portrayed in the psychrometric chart as shown below. This green zone is called comfort zone. So with the aid of this chart, we can, if a given temperature is given, condition temperature or points are given, two parameters are known, how to bring it down to comfort zone, such numericals can be solved. Okay, either we may have to do humidification or heating, or we may have to do cooling and dehumidification. So whatever we do, so what is the energy requirement, or you can say how much heating, how much heat load is to be given, or what is the capacity, kind of thing numericals can be solved. Okay, to bring the system to comfort zone. Okay, so that is the extension of application of the psychrometric chart. Okay, so for example, we have a outside air, is atmospheric air is 35 degrees Celsius with 60% relative humidity, and it needs to be conditioned by cooling and heating so as to bring the air to within the comfort zone. Using the psychrometric chart, neatly plot the required air conditioning process and estimate the amount of moisture removed and the heat to be removed, amount of moisture to be removed. This capital H1 minus H2, right? So multiplied by m dot will give us the amount of moisture removed. Amount of heat removed is again m dot into small h1 minus h2, where small h1 and h2 are enthalpy from the chart. The amount of heat to be added also can be done. Okay, so this is the chart. Again, we are going to this chart with the comfort zone is mentioned in this chart. So what you can do is temperature is given and relative humidity is given. So we mark that point. Okay, and if you go towards the left, and we have to bring this system to comfort zone. Okay, so how to we can be done? So we have to go this way, and we can adiabatic cooling can be done. Okay, so then we have to again heat it, because it is mentioned there is cooling. Okay, and there is heating also involved to bring it to comfort zone. Okay, so how this can be done, what are the how we can determine the parameters? So what we need is we have to draw the line along the enthalpy lines. Okay, so this comfort zone and that one, and h1 and h2 can be determined. Okay, and what you can do is, this is the representation. They asked you us to draw this line, right? How to, what is the air conditioning or how it is working. So condition can be represented in the chart and diagram as like this. Draw a line, give a arrow mark direction of the thing. The we are doing cooling, sensible cooling. So here we are doing this one, uh, and then we are reducing the humidity, right? Here there is no change in humidity, only cooling is done and dehumidification is done. Okay, so then what happens, it is again heated to get into the comfort zone. Okay, so that process is represented like this. Okay, see from the graph you can mark absolute humidity in the y axis, capital H1 equal to 21.3, capital H2 equal to 9.8, small h1 value in this line around 88 or 89, h2 value around 40, h3 value around 50. H3 is endpoint, h2 is the curve along the saturated line. So from the chart we have absolute humidity initial and final changing from 21.3 to 9.8. Therefore the amount of moisture removed is h1 minus h2 11.5 grams of water per grams of dry air. If m dot value is given, we can multiply, amount of dry air is known, we can even multiply it to get what is the actual amount of moisture removed for a given amount of dry air. Okay, we know the formula, heat added or heat removed is m dot into delta h small h, where it is enthalpy value at initial and final stages. So we are going to find first heat added and heat removed and then heat added. To find heat removed, so initially we have the value 88 and h2 value we get 40. So h1 minus h2 is 48 and m dot is not given, so we can leave as it is because we are writing for, so answer we will be writing in kilojoules per kg dry air. But if mass m is given like 1 kg dry air, we can simply report as 48 kilojoules. Okay, if m dot is any value, you will be getting answer only in kilojoules. Similarly, again there is some heat addition, heat to be increased after heat removal. So that is h3 value we got 50, h2 value we got 40. Refer to the graph. And difference in the value is 10 kilojoule per kg dry air. Similarly, q is equal to m dot into h3 minus h2. So m is assumed to be 1, means we will get q equal to 10 kilojoules. Okay, and amount of moisture removed, heat removed, and amount of heat added can be calculated. Okay, next problem. A hot dry air at 40 degrees Celsius and 10% relative humidity passes through an evaporative cooler. Water is added as the air passes through a series of wicks and the mixture exceeds at 27 degrees Celsius. Using the psychrometric chart, determine the value. Okay, so the two parameters are given, 40 degrees Celsius and 10% relative humidity is given. So with that we can go to the graph. So 40 degrees Celsius is the hot dry air temperature and 10% relative humidity. So this is the 10% relative humidity line and temperature is 40 degrees Celsius. So 40 degrees Celsius and 10% line. So you will be marking a line here. Okay, so 40 degree 10% we have a point. So we have to go to this comfort zone from here. Okay, so to comfort zone, if you look at a line parallel to this, you will have a 45% RH. Okay, so for a given percentage relative humidity 10 percentage and dry bulb temperature of 40 degrees Celsius, if you draw a line, enthalpy line parallel to this comfort zone, parallel to the enthalpy line from the given point, so we had 45% relative humidity as the answer for first part. And similarly, how much humidity is increased from here to there, so we can take the corresponding y-axis value here. What is the thing? You can say it is less than 5, it is almost 10. Okay, so from that we can get the value. So what is happening here, actually we are increasing the humidity and then there is sensible cooling taking place. There is in humidification taking place and then sensible cooling is taking place. That is temperature is reduced from 40 to comfort zone temperature around 27. Okay, so what is the temperature decreased is 40 minus 27, which is 13 degrees Celsius is the temperature to which it is cooled. And what is the moisture addition? If we consider it to be 10 and 4.5, so we get 5.5 grams of vapor per kg being reduced. Okay, so how we get RH? So if you draw imaginarily, you have to draw a line here where it touching this 27 degrees Celsius line. Okay, so parallel to this line. So that what we get. And another question base, what is the maximum temperature that could be achieved? So what is the maximum temperature when you are doing process like this can be done? From this point, you draw a line parallel to this enthalpy line or wet bulb temperature line. So that is the maximum temperature, because till we go to dew point, we can have the temperature, right? So dew point line is this 100% saturation line. So you draw a line parallel wet bulb along the wet bulb temperature or enthalpy line, draw a line parallel to this point, and corresponding value to this 100% saturation line gives us the maximum temperature that can be attained. Okay, so that is so you can report the answer. Please report your answer. So what is the outlet relative humidity, amount of water added, what is the lowest temperature that could be realized? Okay, actually this type of cooler is extremely popular in deserts like hot and dry climates, and it is called as swamp cooler. Okay, in this lecture we have solved some numericals on humidification, how to make use of humidity chart and solve the numericals. I hope you found it useful. And this for humidification numericals we are going to make use in the mass transfer course also. Okay, all the best.